So this is the fourth of 4 videos about P3 Particle Model of Matter from the AQA Physics syllabus. I use this mind map to center our ideas, so you'll see a portion of that on the different slides. This video is concerned with the top left section of this, which is the part regarding pressure. During the video you will see sections which are on a white background, and those are the text from the AQA specification for physics. The syllabus says that the molecules of a gas are in constant random motion. The temperature of the gas is related to the average kinetic energy of the molecules. Changing the temperature of a gas held at the constant volume changes the pressure exerted by the gas. You should be able to explain how the motion of the molecules in a gas is related to both its temperature and its pressure. And you should be able to explain qualitatively the relationship between the temperature of a gas and its pressure at constant volume. This part of the topic is to do with gases. So let's review first of all what we know about the molecules of a gas. So we know that they're going in random directions. What you might not have picked up on is that they are actually travelling at different speeds, and so they have different amounts of energy in their kinetic store. And this is shown in the diagram. You've got them going in all sorts of different directions. Some of them have got longer arrows, some shorter arrows, and that is supposed to represent the different speeds that these particles are going. Now the molecules may collide with one another, and they may collide with the side of the container they are in. Now two things to link in here. Temperature. Temperature is linked to the average kinetic energy of all the molecules. So if I transfer some energy into the gas, the average kinetic energy of the molecules will go up, and therefore the temperature will go up. And secondly, the pressure. The pressure is linked to the number of collisions between the gas molecules and the sides of the container. So what you're supposed to link in here is well, okay, what's going to be the effect of increasing the temperature on the pressure? So in gases, the temperature, the volume and the pressure are all linked together. So if you imagine squashing the sides of a container, that will make the volume get smaller. The volume will go down. But it will also mean that the pressure inside there goes up, because the molecules are going to hit the sides more often with a smaller volume. And if you heat the container, the molecules move faster, giving us a higher temperature, meaning more collisions with the side, so the pressure goes up. So from this you can see that we can make the pressure go up by making the volume go down, or by making the temperature go up. Now that is as far as you need to go in this video if you are taking the foundation level in the exam. If you're doing the higher tier, then you need to continue to the more advanced bit to follow. So the syllabus states that a gas can be compressed or expanded by pressure changes. The pressure produces a net force at right angles to the wall of the gas container. Students should be able to use the particle model to explain how increasing the volume in which a gas is contained at constant temperature can lead to a decrease in the pressure. So here we have a simulation showing some gas molecules inside a sealed container. And so what I recommend you do is that you spend a few moments just following the course of one individual molecule. You should be able to see that its direction and its speed changes from time to time, either when it gets hit by another molecule or when it hits the sides of the container. Now the molecules hitting the side of the container, that generates the pressure, which is measured here. And the pressure here at the moment is 16 times normal atmospheric pressure. The temperature there is shown at 616 Kelvin. Now if I now decrease the volume of the container here to about half of the original, so that's about there, you'll see that the effect is that the temperature there hasn't changed, but the pressure has doubled. So the pressure now is 32 times the atmosphere, and my volume has halved. And we're going to be bearing that in mind when we derive the equation to link pressure with volume. So going back to the original again, so we have a pressure of 32, the volume there. If we double the volume, the pressure has now halved to 16. So in the demonstration there, you just saw that if we halved the volume, then the pressure doubles. So halving one doubles the other. And that then leads us to this important equation here, that the pressure times the volume always gives us a constant number. So in order to keep that constant number, if we double one, then the other one has to halve to keep it the same. Now in this equation, the pressure has got to be measured in pascals. That's abbreviated to PA. And 1 pascal is a newton per cubic metre. And then your volume there has got to be in cubic metres. Now this equation is giving you on the equation sheet, you just have to be able to use it. Now that equation implies that pressure is inversely proportional to the volume, which means, for example, if you double the volume, then the pressure will halve. And that is written P and then the proportional sign and then 1 over V. So you'll see in the table here that I have taken the volume and doubled it again to 8, doubled it again to 16 and so on. And then I have halved the pressure. So I've started at 80, I've halved it to 40, halved it to 20 and so on. Now this is showing pressure inversely proportional to the volume. If I double the volume, the pressure halves. If you plot those figures, you end up with the graph of the shape that is shown there, which drops very, very steeply, and then plateaus off and goes virtually horizontal after that. That is the shape of the graph you end up with for one of the variables inversely proportional to the other one. The test for whether two things are inversely proportional is that you take the coordinates of each point, multiply them together, and it should always give you the same number. In other words, pressure times volume for this one is constant. So if we take the first row, the first coordinates, it will be 180. So if you do 1 times 80, that gives you 80. The second point on there is the coordinates 2, 40. Multiply those together, 2 times 40, 80. The next one will be 4, 20. Multiply those together, 4 times 20 gives you 80. So it's always giving us 80, and the two are inversely proportional. Now you might have thought that pressure times the volume is a constant is a really easy equation. You know, can't be a difficult question. Well, the sort of question you're going to get is given here. you should be able to calculate the change in the pressure of a gas or the volume of a gas when either the pressure or the volume is increased or decreased. So, giving you an example here. So if we have a gas with a pressure of 5,000 pascals occupying 25 cubic meters. If it's compressed to take up 10 cubic meters, what's the new pressure? Okay, now we know that pressure times the volume is a constant. So we'll start by finding out what's the constant. So we do the pressure times the volume, 5,000 times 25 to give us 125. So 125,000 is our constant. Now the new pressure, rearranging the equation, the new pressure will equal the constant, which we've worked out, divided by the volume, which we're told in the question. So we have 125,000 divided by 10, giving us 12,500 pascals. You'll see that's a higher pressure than the 5,000, which is what we're expecting because we have reduced the volume. Therefore, we would expect the pressure to increase. Now, we'll be considering the idea in physics of work in the energy topic, which is P1. So this is just a preview of this. In physics, work is done whenever a force moves through a distance. And it's also true to say that whenever work is done, energy is transferred. And you've got to be able to use those ideas to suggest why certain observations are made. So the example given in the syllabus is pumping up a bicycle tyre and explaining why the pump gets hot. So when you pump up a bicycle tyre, work is being done because energy is being transferred from the chemical store of your muscles to the internal energy store of the gas molecules. This causes the molecules to move faster, which means their temperature goes up, which means the pump gets hotter. So that is the sequence of ideas you need to convey to the examiner to explain why the pump gets hotter.